Ever wonder how AI systems like GPT or BERT understand language so deeply? The answer lies in a revolutionary architecture that's redefined machine learning, the transformer. Today, we're diving into the technical heart of transformers, how they process information, why they outperform older models, and what makes them the backbone of modern AI. Let's break it down. Before transformers, recurrent neural networks (RNNs) and convolutional neural networks (CNNs) dominated sequence modeling. But they had critical flaws. RNNs struggled with long-term dependencies due to vanishing gradients, while CNNs relied on fixed receptive fields, limiting their ability to capture global context. These bottlenecks demanded a new approach, one that could process sequences in parallel and model relationships between all elements, not just adjacent ones. Enter the transformer. Its defining feature is the self-attention mechanism, which allows the model to weigh the significance of every word in a sentence relative to others. Here's the math. For a sequence of tokens, the model computes query Q, key K, and value V vectors. The attention score between two tokens is the dot product of their Q and K vectors, scaled by the square root of the key dimension. This produces a matrix of weights, which are then applied to the V vectors to generate a context-aware representation. This process happens in parallel across all tokens, eliminating the sequential processing of RNNs. But wait, how does the model know the order of tokens? Enter positional encoding. Unlike RNNs, which inherently process sequences step by step, transformers use learned positional encodings added to token embeddings. These encodings, often sinusoidal functions of position, inject information about the token's location. The result is a 3D tensor of shape, which the self-attention mechanism uses to contextualize relationships. The attention matrix with dimensions reveals how each token interacts with every other, creating a rich web of dependencies. The transformer's architecture is built on stacked encoder and decoder layers. Each encoder layer contains a multi-head self-attention mechanism, allowing the model to focus on different aspects of the input, followed by a feed-forward network. The decoder adds a second self-attention layer to attend to the target sequence, ensuring context-aware generation. This design enables tasks like translation, where the encoder processes the source language and the decoder generates the target, all while maintaining global context. Transformers aren't just theoretical, they've powered breakthroughs like BERT and GPT. BERT's bidirectional training uses masked language modeling, where the model predicts randomly masked tokens using context from both left and right. GPT, on the other hand, employs a causal attention mask in its decoder-only architecture, enabling autoregressive generation. These variants highlight the transformer's flexibility, with parameters scaling from millions to trillions, enabling tasks from text generation to code completion. Despite their power, transformers face challenges. Their quadratic complexity and sequence length limits scalability, leading to innovations like sparse attention and linear transformers. Researchers are also exploring memory-efficient variants and hybrid models, combining CNNs and transformers. The future: models that balance efficiency with performance, enabling real-time applications from medical diagnostics to autonomous systems. Transformers have transformed AI, but their journey's far from over. By mastering self-attention, positional encoding, and scalable architectures, we're unlocking new frontiers in machine learning. Whether you're a researcher or a curious learner, understanding these principles is key to navigating the next wave of AI innovation. Stay curious and keep exploring the code behind the magic. Thanks for watching. If you want to dive deeper into the math behind attention mechanisms or see code examples, hit the link below. Subscribe for more deep dives into cutting-edge AI research, and let me know in the comments what topic you'd like to explore next. See you in the next video.